Okay, welcome back, ladies and gentlemen. You should be in measuring heat flow calorimetry, which should be around page 8 in your unit packet. So first we're going to talk about coffee cup calorimetry. We talked about that already in the videos that I had you watch yesterday. Measuring heat flow of a solution in styrofoam polystyrene cups at constant pressure. Specific heat of water hasn't changed, 4.18 joules per grams degrees Celsius. What I do need to talk about is this piece right here, very important, card worthy. You might write it down on your formula card if you're keeping one. Q reaction equals negative Q calorimeter. So whatever we get out of the calorimeter, it is equal in magnitude, same value, but opposite in sign. Okay, so heat flow of the reaction system is equal in magnitude, but opposite in sign. So when we apply this formula down here, we're going to put Q reaction, and we're going to end up putting a negative symbol in, because what we get off the calorimeter would be opposite in sign of what we get through the actual math. So keep in mind that in a reaction, exothermic is less than 0. So therefore, Q calorimeter will be greater than 0, right? If it's an exothermic reaction, it's going to have Q reaction less than 0 or negative. Q calorimeter will be greater than 0. If its reaction is endothermic, Q reaction is going to be greater than 0 and Q calorimeter will be less than 0. So to keep that all straight, just know when you're looking at a chemical reaction, we're going to change the MC delta T slightly by saying Q reaction, and we put the Q reaction here to indicate that, and then we put the negative symbol in here to take care of that piece. Okay, so I'll demonstrate that in the next example. Okay, so example 10, when 10 grams of calcium chloride is added to water, 50 grams of water and a coffee cup calorimeter is dissolved, then calcium chloride breaks down into calcium ion and 2 chlorine ions, and the temperature rises from 25 to 28. Assuming that all heat is given off, the reaction is transferred to the water. Calculate Q for the reaction. So you are going to, I have a temperature change here, so that's an indicator that I need to do Q, and I have a chemical reaction, so I'm going to do Q reaction equals negative M times C times delta T. Now, rarely do we ever keep delta T as delta T. We're going to really think of it as negative M times C times TF minus TI. Okay, so now how do I know to use this negative symbol? Well, we're going to say Q reaction because it's talking about a reaction between calcium chloride and water. This would be an exothermic reaction because the temperature is going up. Okay, but the reaction itself, right, is going to give off heat, so we expect our answer to be negative when we're done. Now, the mass, the stuff, all of this stuff here has to be let me try that again, has to be obtained from the same chemical. So I can't plug the mass in of one thing and this, specific heat of another and the temperature change of something else. All three, mass, specific heat, and change in temperature, must be of the same substance. So the substance that we know a temperature change of is water. So therefore, we have to use the specific heat of water and the mass of water in this problem. Let me say that again. When I use a Q reaction, everything about this has to come from the same chemical. So the mass has to be of the same substance as the C is, as the change in temperature is. What we know change temperature was the water because we had it in a coffee cup calorimeter. Okay, so we have to use everything about water in here. So we're looking for the mass of water, which is 50 grams. So we're going to take negative 0.50 grams times 4.18 joules over grams degrees Celsius. My TF is my ending temperature, 28.51 degrees Celsius, minus my TI, 25.00 degrees Celsius, and then we're going to get an answer here. Okay, so we got 50 times 4.18 times parentheses 28.51 minus 25, close parentheses, and then I can't forget about that negative I have out there. I just didn't put it on write it on my calculator. We get negative 733.59 joules. Now why joules? Because grams would have canceled, and this difference, degrees Celsius, would have canceled when I subtracted that. Okay, so negative 733.59 joules is given off. It makes sense that it would be heat. It would be given off because the temperature increased, so it would feel warm to the touch. Okay, part 2 of this question, it says calculate Q, so calculate Q or heat when 1 mole of calcium chloride dissolves. Well, we know what happens when 1 gram of calcium chloride dissolves. We know that when we put 1 gram into this calorimeter with 50 grams of water, there's a temperature change this much, okay? So what we need to think about is, what if I changed this value, right, and I still kept it in 50 grams, then this temperature change is going to go up or down depending on what I change that value to. Put more in, might heat it up more. Put less in, it might not heat up as much. So what's key here is that we know a relationship now between how much we put in, 1 gram of calcium chloride, and versus how much we get out, assuming that we keep the mass of the water the same. So if I put in 1 gram of calcium chloride, I'm going to always get out negative 733.59 joules of heat, or 733.59 joules of heat will be released. Okay, so now I change this, it's going to go up. So here's how we do this piece when I ask about a mole, because a mole is not the same thing as a gram. They're different quantities, right? So we're going to have to do a little bit of stoichiometry, kind of, not really stoichiometry, but relating the balance, relating what is going on in the equation to this. So we're going to start with what we're given, 1 mole of calcium chloride. And we know that for every 1 mole of calcium chloride, because what are we trying to get to? We're trying to get to Q, so we're trying to get to joules, right? And we have a relationship now between how much we got out and what we put in. We put in 1 gram and we got out negative 733.59. So we're going to figure out what the molar mass is, because we got to get to grams to be able to get to joules here. So we're going to take our calcium chloride 40.08 plus 35.45 plus 35.45. So we have 110. Okay, this is 110.98 grams of calcium chloride. Where did I get that? Periodic table, right? Why am I doing this? Well, I want to know what Q is for 1. So I got to get to joules, right? And I'm starting with 1 mole, so that's my starting point. And then I know from my equation up above, my reaction that I did, that for every 1 gram of calcium chloride, so I can put that here, 1.00 grams of calcium chloride, we release negative 733.59 joules. So this is a relationship just like this relationship, right? Periodic table relationship. Now we have established from our math up here a relationship between in versus out. Okay, and so units cancel, and we have joules of calcium chloride left. So we're going to take and we're going to say 1 times 110.98 times 733.59, and then divide by 1, which is kind of redundant, and we don't need to really do it on the calculator. So we're going to get negative, I just didn't say it when I wrote it on my calculator, I just use it at the end, negative 814, no, I can't read that number, let's try that again, 81413.82 joules. So that's how much joules would be given off if we use, instead of 1 gram, 1 mole of calcium chloride. Okay, so now we're going to look at something called heat capacity. When we were doing this problem, we looked at specific heat. We were given a specific heat for water. We used a specific heat of water. A clue here is that you see the word coffee cup calorimeter. So if you see the word specific heat or the word coffee cup calorimeter, then you know you're using this formula for Q reaction. Q reaction equals negative M times C times delta T. When we use a bomb calorimeter, we're going to use a slightly different formula. We're going to do Q reaction equals negative. This is a capital C calorimeter, so the heat capacity of the calorimeter, different than specific heat. We talked about those definitions in the beginning, times delta T. Now this can be lowercase or uppercase t, it really doesn't matter. But what's important is you understand that you can only use this reaction, this chemical now let me try that again. You can only use this algebraic equation if you see the word bomb calorimeter in your question prompt or the word heat capacity. If you don't see heat capacity or bomb calorimeter, then you're going to be using this one, Q reaction equals negative MC delta T. If you see the word heat capacity, or you're given a heat capacity, or you see the word bomb calorimeter, you're going to use Q reaction equals negative heat capacity of the calorimeter times delta T. Now, these are the 2 videos that you watched before, so I'm not going to click on those. Okay, so Q reaction equals negative M times C times delta T. Q reaction equals negative heat capacity of the bomb calorimeter times delta T. And don't forget that Q reaction is equal in magnitude but opposite in sign to Q calorimeter. So that's why we just kind of keep it as Q reaction and don't worry about ever solving for Q calorimeter. Okay, you may see some of those in textbooks, but that's not how we're going to do it. We're going to handle it in this way. Make it a little bit simpler for us. Okay, all right. So this is just an example. You saw that in the video of the bomb calorimeter. And now let's do problem 11. Fructose is sugar commonly found in fruit. A sample of fructose, C6H12O6 with a mass of 4.50, is burned in a bomb calorimeter. So we're going to put it in that system that you saw the video of. The heat capacity, so that should give you a indicator of what kind of what kind of algebraic equation you're going to write. The heat capacity, okay, hint there, of the calorimeter is that. the temperature of the calorimeter rises. Okay, so we have everything we need. So we're looking for Q, as it asked for, and it says Q for the combustion of 1 mole, okay? So we're going to figure out what that is. So we're going to say Q reaction equals negative C times delta T. Now, why did I leave out mass? Because I saw the word heat capacity. That tells me, therefore, I also saw the word bomb calorimeter. If I see either or both of those words, either or, I know I'm not going to include mass in the reaction. Pardon me, I keep using that word, I apologize. In the, I'm not going to use the mass in the algebra formula. I want to pick the other one because this is the one we would use with bomb calorimeter. Okay, so we are going to take the heat capacity, so 2.115 times 10 to the 4th joules over degrees Celsius times your change in temperature, 27.71 degrees Celsius minus 23.49 degrees Celsius. And I accidentally forgot my negative, so you always want to go double and check. That's what I did. That's why I noticed it. So 2.115 EE to the 4. I'm not going to worry about that negative. I'm just going to slide it in at the end. Times 27.71. I apologize. I should have said what I did. I'm taking 2.115 EE to the 4th times parentheses 27.71 minus 23.49. So I'm just using that equation. And I get in here negative 89253 joules. Okay, so that's my Q reaction. But this is what? What's my in? Because this is my out. That's how much heat came out. Okay, or heat was either given off or absorbed. In this case, given off because it's negative. That was the heat transfer right here. What did I do to get this much heat transfer? This is how much I put in. And then I got this much out. Okay, so we know from this equation and the math we've done so far that we'd get negative 890,000, okay, joules if we put 450 grams of that fructose in. It wants to know what is Q for the combustion of 1 mole of fructose. So we're going to take 1 mole of C6H12O6 and we're going to go to joules. Now we have that new relationship we've established in this unit, right, between the out and the in. So 4.50 in and 89,253 out. So I can say for every 1 mole of C6H12O6, I'm going to figure out the grams of C6H12O6. So I'm going to take 6 times 12.01 for carbon plus 12 times 1.01 for hydrogen plus 6 times 16 for oxygen, and I get 180.18, 180.18. This is just the periodic table number. And I know then for every 4.50 grams of C6H12O6, we released, or 89,253 joules is released. So now look what we have in terms of units. Everything cancels, and we do have joules starting with 1 mole. So we're going to take 180.18 times 89253, divide by 4.5, and we get negative 3573690 joules. I just left off my decimal places. I just want to point out that, again, we were able to establish a relationship between the last two problems, example 10 and this one, between what we put in and what we get out. What we put in terms of mass in this case, and what we get out in terms of heat transfer. Okay, so looking at 11b, in earlier times, ethyl ether was commonly used as anesthetic. So lots of words here. Now, here's something that's really sneaky that chemistry problems like to do. It gives you a number in words, so be careful and look for that. 5 milliliters of ethyl ether is burned in a bomb calorimeter, so I see the word bomb calorimeter, so now I automatically know Q reaction equals negative C delta T, and this is heat capacity. So we got negative, we're given the heat capacity right here. That's another hint. We're given heat capacity 10.34 kilojoules per degree Celsius. Then I'm going to change in temperature here, so 39.70 degrees Celsius minus 23.50 degrees Celsius. So we're going to figure out what that Q is. So 10.34 times parentheses 39.7 minus 23.5 close parentheses. And we get negative, because I just didn't put it in my calculator, I just left it there so I didn't have to mess with it, 167.508 kilojoules. Okay. And we can go from there then. Okay, so that's kilojoules. Why kilojoules? Because our bomb calorimeter was in kilojoules. So this is how much we get out, right? This is our out. And we're going to put this much in. That's how much we put in. If we change the amount in, we'll get a different amount out. Okay, because the temperature would change. Okay, that's how we know that. So the temperature would change most likely unless we hit the equilibrium piece, okay, or a piece where we have a limiting reactant situation. Really is the better phrase to use here. But at some point, right, whatever I put in, when I change the amount I put in, that's going to change what the temperature changes. Therefore, it changes the amount out. Okay, but it asks for what is Q for the combustion of 1 mole of ethyl ether. So we're going to take 1 mole of C4H10O. And we are going to then take 1 mole of C4H10O and figure out what the molar mass is. So 4 times 12.01 plus 1 times, let me try that again, 10. 4 times 12.01 plus 12, let's try that again, 10 times 1.01, if I can hit the right number with my calculator here, plus 16. So I get 74.14, 74.14 grams, periodic table number C4H10O. And I know for every 1 mole of C4H10O, okay, oops, that's not the right number, I apologize. My brain is thinking 3 steps ahead here. Let me fix that. Okay. Now, I cannot go here. I cannot put in 5 milliliters down there because that unit's not going to cancel if I do that. So why I'm talking here, I want you to look at that word problem and think about what we got to do. Well, we're going to have to use the density, aren't we? Because I can't go put 5 milliliters here. It won't cancel. Yes, 5 milliliters equal to this, but I can't put 5 milliliters here. My unit wouldn't cancel. So instead, we're going to say 0.714 grams of C4H10O is equal to 1 milliliter of C4H10O. Now that's using density like we used in the last unit. Okay, you got to be able to write that density. Remember, we're going to have to write this as a ratio. We're going to keep the grams with the top unit and with the number, the grams because it's on top with the number, and put 1 milliliter on the top. And then I flipped it so that the unit would cancel the way I need it to, right? As long as I keep that with that, I'm good. So now I can say 5.00 milliliters of C4H10O is equal to what we put out, 167, what was put out, 0.508 kilojoules. So now we're going to multiply the numbers going across the top and the bottom and divide. So 74.14 times 1 times 1 times 167.508 negative, divide by 0.714 equals, divide by 5 equals, and we get here a final answer of negative 3,478.72 kilojoules. So that is very similar to the last problem with the one added piece of needing to use density to be able to use our in versus out. Okay, next I need you to find the worksheet. It might be a single worksheet or it says FA bomb calorimeter. And there's an A, B, C, and D on one side and an A, B, C, and D on the other side. So FA bomb calorimeter. Okay, you are going to pause this video and you're going to try one on each side depending on what desk tag you are, what color you were assigned. Okay, so A, B, C, or D, pick one of those. Okay, and there are the answers for you. Notice that those answers are in kilojoules. Okay, please get on a Google Meet or reach out if you're struggling with this. If it's 7,000.